Let's talk about the invertible matrix theorem, the key theorem of any introductory linear algebra course. Let A be an n by n matrix. The following statements are equivalent. That means if one of these statements is true, they're all true. And if one of these statements is false, they're all false. A is invertible. The reduced row echelon form of A is I, the identity matrix. A can be written as a product of elementary matrices. AX equals 0 has only the trivial solution. During this course, we will add more statements to this list, so write this on the back page of your notebook. This will be the most useful theorem of the course. So this, don't just bury this in your notebook someplace. Write it on the back page. So again, here is the invertible matrix theorem. Let's look at an example. So let's illustrate this with the matrix A equals 1, 2, 3, 2, 5, 3, 1, 0, 8. First, A is invertible. That's true. In a previous video, we found that A inverse is this matrix. And so because this is true, all the other statements are going to be true. The reduced row echelon form of A is the identity matrix I. Well, that has to be true by the invertible matrix theorem. But that's true. This is how we found the inverse, by reducing A to the identity matrix. A can be written as a product of elementary matrices. That's also true. We used elementary row operations to transform A into I, which implies that A is a product of elementary matrices. AX equals 0 has only the trivial solution. This is also true. The reduced row echelon form of this augmented matrix, here's A, and here's the last column. So the reduced row echelon form of this matrix, this augmented matrix, is just this one, which implies that x1 equals 0, x2 equals 0, x3 equals 0. So AX equals 0 has only the trivial solution. So again, here's the invertible matrix theorem. What we're going to do is sketch a proof of this. We're going to show that A is invertible if and only if the reduced row echelon form of A is I. So in other words, we're going to show that these two are logically equivalent, that the first one is true if and only if the second is true. Okay, so A is invertible if and only if the reduced row echelon form of A is I. Here's why. Think about how we find the inverse of A. We write A, we write A on the left side of a matrix, we write the identity matrix on the other side, and then use elementary row operations to reduce A to I. If we can do this, then A has an inverse. And if we can't do this, then A has no inverse. Thus, A is invertible if and only if the reduced row echelon form of A is the identity matrix. Okay, the reduced row echelon form of A is I if and only if A can be written as a product of elementary matrices. So now what we're doing is showing that these two are logically equivalent, the second and the third statements. Okay, so again, we're going to show that the reduced row echelon form of A is I if and only if A can be written as a product of elementary matrices. Suppose the reduced row echelon form of A is I. When we use elementary row operations to transform A into I, it is the equivalent of multiplying A by elementary matrices. First E1, then E2, then blah, 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 then E sub n minus 1, then E sub n, and that all equals I. Thus, E sub n minus 1, blah, 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 E sub 2 times E sub 1 equals A inverse, because this is the matrix you multiply by A in order to get the identity matrix. So what I've just circled is the inverse of A. And if you take the inverse of both sides, you get E sub n minus 1, blah, 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 E sub 2, E sub 1 inverse equals E1 inverse, E2 inverse, blah, 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 E sub n minus 1 inverse, E sub n inverse, and so that has to be A. Because again, we're just taking the inverse of both sides of this equation. Okay, so A is invertible if and only if AX equals 0 has only the trivial solution. So now we're showing that these two are logically equivalent. And again, I didn't prove the if and only if part for the previous proof, but you could easily do that. I proved in one direction. Proving it the other direction is fairly simple. It's done in a similar fashion. Okay, so let's show that A is invertible if and only if AX equals 0 has only the trivial solution. Suppose A is invertible and AX equals 0. Multiply both sides by A inverse. A inverse AX equals A inverse 0. Well, these two cancel and you're left with the identity matrix, and A inverse times 0 is just 0. Notice that this implies that x equals 0. So the only solution is x equals 0. AX equals 0 has only the trivial solution. Conversely, suppose that AX equals 0 has only the trivial solution. There are no non-trivial solutions, so there are no free variables. All the variables are leading variables, and thus the reduced row echelon form of A must be I. And it's got to look something like this, if you're talking about a 3 by 3 matrix. By the way, if a matrix is not invertible, we say that it is singular. If it is invertible, we say that it is non-singular. For example, A equals 1, 2, 3, 2, 5, 3, 1, 0, 8 is non-singular because it has an inverse.